Hello, my name is Gabriel, and today I'm going to go over Lab 3 bar magnets. The objective of this lab was to measure the distance-dependent magnetic field of a small bar magnet and compose measurements using Biot-Savart's law. As an overview, there was a small correlation in an order of magnitude between the computational and analytical solutions for the magnetic field, even though those differ a little bit from each other. The fundamental principles used for this lab were magnetic field formula, Biot-Savart's law, and magnetic field superposition, wherein the magnetic field of magnets can be summed to get a net magnetic field. The formulas used are shown on the left, and the materials used were a Tesla meter, a magnetic bar, a Lab2 Excel spreadsheet, pieces of tape, and a ruler. The experimental setup is shown in the picture, where our the system is the magnetometer. The surroundings are considered to be the bar magnet and Earth, and for the initial conditions, our phones are placed on the y-axis only. These are the experimental results obtained in this lab. The data is shown here in Lab2 spreadsheet, and a correlation is shown on the right. For the calculation section, we first define the two magnetic field formulas as equal to each other to then get an equation for mu, as shown here in the top left. From the graph, we can then obtain the slope to get the constant n, which is negative 1.3. And then we also obtain k by getting the intercept, which was 2.94. And then e to the 2.94 equals to k, which is 19.28. The mu was calculated, assuming r is equal to 1, and a value of 9.59 was obtained. These are our observations. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, which was true. And as it moves closer, the measured x component actually increases, it doesn't decrease. The position does have an effect on the magnetic x component of the field. And as the magnetometer moves closer to the magnet, the x-axis component increases. This is a picture of the computational model used with the applied constants. And these are the model results. The magnetic field at 45 degrees at distance d was obtained to be 2.71 to the negative 5. As a conclusion, the computational result largely differs from the analytical results, and these could be due to sources of error, such as human error, as maybe we did get wrong measurements recorded, or there were some calculation rounding errors, and it was also not reliable. We were moving phones using our hands, so this could shift the phones in a way we didn't want to. There could also be equipment error, as in the equipment was old, so it could not have been calibrated before. And also other objects in the lab could have been interfering with the magnetometer. For our discussion, what if you hadn't oriented your experiments to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? If we didn't do that, basically Earth's magnetic field would interfere with our measurements, and the actual measurements would be off. They would be a little higher than they should. What if you were to stick two identical magnets together end to end? This would change as in the magnet would be as if it was a combined stronger magnet, and this will be reflected in the calculations by multiplying the values by a factor of 2. Thank you.